afternoon again. Professor Edmar Puccini will talk to us a little bit more about data analysis,
Yes, and machine learning
machine learning,
stuff. Yes.
and so enjoy yourself.
Thank you very much, Gabriela. So the idea for this afternoon is try to continue the discussion that we have during the morning, but with some hands-on section. So I put inside my GitLab one file that I want to ask you to open. You can open the Google Colab directly. This lab3 file, the Python notebook. So just to explain the exercise that I want to explore with you. So the idea for this exercise is try to see examples for the neural network definitions, and we considering this application for gamma hadron separation data from simulated data from the Magic Telescope that we can have open access. And the idea also is try to explore the changing of hyperparameters for the neural network, right? So like the number of epochs, different strategy to stop the training, number of the hidden neurons, optimization algorithm, and loss function. So that's the idea. I want to highlight all of these points. It's very important for you to try to follow, and you can change the definitions and also restart the training and restart the commands inside the Python notebook. So I can wait just 1 or 3 minutes. I don't know if you already have the files opened inside the Google Colab. It's okay if you... Yes. Maybe it's included in the agenda, let's say. It's the same link. Let's see. Yes, in my GitLab repository, you can just click here for the first day. You managed to see? Okay. Yes, the lab 3. Good. So just to explain the problem, we already have a short discussion during the morning. So basically, we have this open data that comes from the Magic Telescope. So basically, the idea is to try to identify gamma ray events out of a charged cosmic ray background. Basically, it's composed by hadrons, and this is a Cherenkov telescope. So usually these signals is the band of very high energies, gamma ray astronomy. So basically, we have some geometric features of this image that we have projected inside the detector, and we will use this information to try to provide a separation using this machine learning machinery. Here on image, it's very interesting. So here it's a gamma-like signal. So here, basically, we expect just EM components in the atmosphere, so we have a more consistent shower. But when we have hadrons or muons, so we have a very different signature. So how we can use this kind of signature to produce one binary detection classifier to select a signal and background. That's the idea. So it's very common in Cherenkov telescopes, and also in signal imaging processing. This feature extraction strategy called the HELAS parameters. So basically, we can try to describe this signature here as an hyperbolic, and also we can try to explore the angle of these deposits, the range of these deposits, and also projections in some different axes. This Hillas parameter is very interesting because we can describe the signature in one way that we can evaluate your distributions and compare it with signal and background samples. So let's to execute here is just to install the CCI Keras. This is a package to use scientific stuff from Keras. Sorry. Yes. We have the microphone somewhere. I cannot see anything from here.
When we have to think about to work with machine learning, and when we can think about an algorithm, uh, some steps to identify, because looking for this image, I'm thinking, okay, maybe I can create, I don't know, an algorithm to do this identification instead of training a AI model.
Mhm. Yes, it's a very interesting question. Why we need to use one AI model instead to look just in these variables? So looking for just for that variables, we have at least two strategies. Rigid cuts. Basically, we can have. It's a very nice question because all of this machinery of the machine learning was based on these limitations. So imagining that we have this parameter here from like this deposit of the shower. So let's define, for example, this distance here and d2 like a variable for that we can define as discriminant. So if you compare to the different the energy deposits, so we expect that for the some hadrons we can have uh, one different shape for these variables. If we provide some statistical analysis, so maybe we can have this for signal, right? And we can have this for background. So I will call here hypothesis 1 and hypothesis 0 for signal and background. So we can define here based on this shape our threshold, right? So I wanted to build a tight threshold. So I wanted to have more pure sample. And then to have this more pure sample, I wanted to reject more background, right? So I will define my threshold here, for example. So I know that uh, below this threshold, I will classify as background. After this threshold, I will classify as a signal. In that case here, I have a low quantity of examples for signal, but I remove a lot of the background. So I have a tight criteria for that. Okay, now I want to get more information, but I will sacrifice the rates for the background. So I will define my new, it's a threshold 1. I will define my threshold 0 here. So I will collect more data because when I'm doing the data taking, I will get more data. But the purity of this collected data is not so good because my threshold is very poor in that case. I need to define by hands a lot of thresholds to have distributions to analyze the data. So I have the impact here on the uncertainties because if I'm getting a lot of background in this distribution, you have a more contaminated sample. So my uncertainties will fluctuate. But in that case here, I can select this type threshold. I will reduce the background, but I have a low quantity of samples to analyze, so I cannot fit the models and so on. We need a trade-off. I can set a lot of these variables, and I can define different thresholds, and we can define a strategy that we usually call it the cut-based. So using this sequence of analysis, I can try to get one sample based in the shape that I know. It's not very powerful because usually doing these mechanisms, I cannot provide or investigate the correlation between all of these variables. Because look at me, you can agree with me that this G1, for example, have some correlation with this axis here, right? For one specific signal. So we are providing different measurements for the same signal. Basically, we are trying to describe using different measurements for the same signal. Of course, we have correlation. So if we define here H1 and we define the H1 dot for this variable, so we have a new variable that, for example, for signal we have this variable, and for background we have another one. So we know that this variable here have correlation with another one. I can build one strategy to explore these correlations, like the likelihood for all of these variables. So it is more powerful because I will try to build one statistical function that combines all of these statistics here. Of course, here I'm that driven, so I need to fit everything. So I can build one likelihood to have a discriminant rule considering all of these variables. So I will have one likelihood function that basically I will enter with all of set of these variables to apply one decision rule if I approve or not this variable. All of these procedures we can apply without machine learning, based on just the statistical correlations. Usually, if we use one machine learning algorithm to try to catch everything, at the end of the day, we can extract the rules based on the likelihood. Because during the training, basically, we are trying to estimate one function that have the compromise between the signal and background, making decision rules in the hyperparameter volume, basically. So we are trying to build one likelihood function to make one decision choice. So with more tools using the machine learning, because we can change the optimization algorithm. We can try to include on a strategy for validation. We can improve the number of layers to try to have more performance or not, including more neurons. So we have more flexibility that usually we can get more more good surface for this kind of separation. It's very important to consider that this strategy here it was very used in the particle physics experiments, for example, because we know about that. We know that how these PDFs here have your behavior. We know about that because we have all of the definitions for the sensors. We define and also the variables. But for the machine learning, we have this black box here. So that's the mission for us as physicists, for example, and we using machine learning, how we can take advantage of this kind of acknowledgement, and how we can implement the machine learning algorithms. After that, how we can explain it. So if we solve this problem, I think we will go a step further in terms of usage for machine learning app. Too much words, but I think is that. But it's a very nice question because all of the calorimetry science was built looking for these single variables because we know about the sensors, we know about the shower profile, for example. Good. Uh, I execute here to install the SCCI Keras. I don't know if you managed to do that. And this command here is to install the repository. So from the UCI machine learning repository. And I think just to install the TensorFlow that you can use and all of the tools. So for those that never use this Python configuration for machine learning, just small words here. Basically, we use this NumPy and pandas like we saw 2 years ago to handle the data. And all of TensorFlow tools to configure the neural networks architecture, right? So TensorFlow is the main today. We have the PyTorch also, but TensorFlow and PyTorch is the main tools to configure neural networks in Python, let's say. And you can use you use this function like a sequential and dense to configure the blocks of the neural network. So the internal blocks, like the input layer, the middle layer, and the output layer. And the scikit-learn is just the tool that we use to handle the data to do the cross-validation procedure, for example, and to provide the normalization of the data and so on. So we have these three main features, or let's say three main tools to use during this exercise. So let's to take a look on data first. It's very important to look on data before to start any machine learning application. And here in this code, basically, I'm getting the input variables in this line 7 here. So we are organizing in a single vector all data that we have, or single metrics, let's say. And the line 8 here, basically, I am including the targets that which means the labels that we discussed during the morning. So in that data here, it's the Monte Carlo simulation. We know the sample that is associated with the class 1 signal, and we know the sample that we have hadrons associated with the class 0. So we have the annotated target and annotated labels. We are accumulating this vector here in UI, and the idea is just to look on that variable. So we have here the description, and we have, I think, 10 variables, if I'm not wrong. Yes, 10 variables and the class. So we have length, width, size, just geometrical variables about this cone. And we have a very nice paper that describes how we can compute these variables. It's very simple. Basically, it's just the projection of these parameters here in the axis, and the distance from the most highest energy pixel from the origin and so on. So it's a way to describe geometrically this shower description. Okay, here the description of basically which means which of these variables. Ricardo, and also the units we have in millimeters. We have a log distribution for the content of the all of pixels, degrees, and millimeters. So it's interesting to define this. Also to rely that we are combining different variables with different units. So it's not so common to do that using the likelihood or cut-based strategies. Good. So here this cell is just to split in the data set. Here we are doing, basically we are splitting the data using this train test split function. And basically we have the input data that we put the all of data that we collect for the data set. We are passing here the labels, and we are defining the size of the test data set. We are taking 20%, and it means that we have 18% to use as training. And we have here, is just to provide the labels for this separation, because we needed to split the test and training. So we need to make sure that in the test sample data set, we have this properly annotation for the label for this subsampling. And we have here just one seed to memorize this selection. So if you rerun again, we split in the same way because we are using the same seed, just a seed to keep the results, or the results for the splitting testing data. So basically here we are defining just one time the samples for train and samples for test. Uh, and here is just the data manipulation, because we need just to convert or make sure that all of these samples have 32 bits, and we are organizing the same type of data to start the training. Good. Let me see if we have more important things to discuss here. So it's different if that we discussed during the morning, because during the morning we discuss, okay, I don't believe in this procedure. I needed to do one cross-validation procedure. You needed to split the data 10 times, and I can use 9 folds to train and 1 fold to test. After that, I needed to rerun again, mixing the folds. In that case here, we are just splitting one time. We discuss about that afterwards. Good. In the next step, basically, let's to take a look on the distributions. Basically here, I'm trying to make histograms for the f-length variable. So we can see here, I think we explain a little bit with this example. Basically, we have a distribution for signal, right? You can see, you can see. And we have a distribution for the background. So we could set up one threshold here to select background and signal, but probably below that we have a lot of intensive background, so we lost a good part of our shape for the signal. So we can see one separation, but it's not so huge. You wanted to ask a question? It is from the measurements, directly for the measurements. So we have all of the signal and background data, and to look just for one variable, we have this separation. But you can ask again just to record. As I mentioned, in that case here, this histogram is just for the measurements. I don't have any separation here. Just look in the data. How, if you remember well, the f length is the variable. Let's see. F length, it's the major axis of the ellipse. So it is that one. So just looking for that variable, we can see something like that, but we don't have any strategy to provide any separation. Just looking at that, we can say, okay, maybe we can build one classification because we have a clear separation here. But if we put one rigid cut, basically defining that after this threshold, all the samples will be background. So, okay, we are right. But below this threshold, if we decided that all the samples will be a signal, we have an intensive background contamination because many samples is still there. So we can use that information to try to build the classification, but considering rigid cuts, I don't think it's a good strategy. The same for the f width. So f width is the variable minor axis of the ellipse. So I think that one minor axis. So we expect for the photons. For photons, we expect more concentrated, right? Because the ellipse for photons is more concentrated. So this value is for photons is very close to lower values if compared to the background.
Sorry if I didn't pay attention, but what are you considering as signals and backgrounds? Signals like photons, hadrons?
Yes, signals is photons
Okay.
and background hadrons. Photons if photons in final state, but come from hadrons.
Okay. Okay.
It's a Cherenkov telescope. Basically, once we have a extragalactic photon entering the atmosphere, basically the projection of this shower is measured by the Cherenkov telescope. But when we have hadrons, hadrons produce a lot of photons, but probably it's not extragalactic particle. We have some radiation for
Okay.
close to the atmosphere.
So this background is mimicking the photon signal, but it was created by a hadron.
Yes,
Okay.
exactly. And these photons, so the signal usually for very high energy experiments can be for supernovas and neutron stars, for example. It's a clear signal for extragalactic objects. And the hadrons, okay, we have hadrons everywhere, so we can perturbate this identification. In that case, here is easy because we have the annotation from the Monte Carlo simulation, so we can at least look in these variables. Good. So here we have how we can define a neural network using Keras. Basically, we need to build all of the intermediate sequence for the neural network, right? So let's try to build one simple neural network. Basically, we have 2 layers with 5 neurons that we will fed these 5 neurons using the data that we have. So this data have 10 input variables, right? F length, F width, and so on. So in that case here, we have in the input layer basically 10 connections per neuron, right? So we will build something like that. And for each connection, we have one weight. So we have the weight for the neural 1, the weight 1 for the neural 1, the weight 2 for the neural 1, until the variable number 10, right? So it is the input layer. And in that case here, we have just one middle layer, right? That we have this second layer, basically. and we have the output. So each neuron, we have the initial state condition that we call it bias. So just to put B here. How we can estimate the number of parameters? Basically, we have 10 input parameters times 5 neurons as input. So in this input layer here, we have 50 parameters to optimize. We have more 5 parameters here. So plus 5. And we have 5 bias to optimize, right? And we have just one neuron of output, so we have just one bias to optimize. So we have here 61 parameters to optimize using just one layer. So we have a optimization any dimensional space to optimize now. So we have a lot of parameters with small units to organize here. In that case, we need to define the input layer. So basically, we define a model to add dot add and the dense layer. When we call dense, basically we are including all of these weights. And we are defining also the activation function. So we are using this hilo activation function. Basically, when we have 0 for values before 0, and we have a 1 after that. And we are defining here the dimension of input. And we are defining the second layer that we have just one neuron, compiling everything. And also we are defining here the fitness function to optimize. Here we can use different fitness function like mean square error or callback library divergence or binary cross entropy. So we can use depending of the problem. So I put here just the binary. And the different optimization algorithms, we have a family of these algorithms. I put here the more recent one, Adam. And the metrics, we can define some metrics to monitor during the training. So here we provide the accuracy, basically is the ratio between the right prediction and the wrong prediction during the training. That's it to define a small neural network. So we have here this estimation that we did, right? Basically, we have the 55 parameters to optimize and also 6 bias to optimize. Yes.
Just a question. Can you customize this logs function, or you just choose from a set of
Yes,
previously defined ones?
you can customize. Using the TensorFlow is not so straightforward, but you can. Exists some extra tools that you can define your curve to optimize, but using PyTorch is more easy because you define by hand the function that you want, and that's it. It's very interesting exercise to do. Yeah. So here, if I remember well, we not parameterize anything in terms of a number of epochs, number of strategy to stop the training. So basically, the model gets the standard parameterization. So running 15 epochs and stop the training. We can control that, basically. We can try to investigate, because why we needed to take care about that? Imagine that we have here the loss function. So let's to use the mean square error, for example. So I wanted to minimize the error, right? And then for each epoch of training, I present the data for training, I estimate the error, and then I adjust the weight. So I want that for the training to have something like that, right? I want to minimize the error. This is for training, but if you remember, we split also for one subset for the validation samples, and we can check this profile. Let's to take as example that basically we have here the validation curving function of the epochs. Val and training. So during the optimization procedure, we have here basically the error being minimized. Okay, it's good. But sometimes we can have this behavior here, which means that once we have the time spending or the epochs is evolving, basically my model is is getting more specialized in the training samples. We have a vicious here. Basically, my model is learning just the features in the training subset. It is not possible anymore to estimate the same performances when we have an input data that not belongs in the training subset. So we needed to monitor the training to avoid this kind of behavior, like called overfit. And then if we stop the training here, basically we can avoid this behavior, right? So how I can do it? Basically, I can implement one strategy to, if the fitness function don't improve after like 10 times of epochs, we stop the training. We call it this strategy like early stopping. So we stop the training to avoid the overfitting. It's very important because when we split the data set, training, test, and validation, we don't know about the content of these subsets. So we needed to evaluate the training during the optimization procedure. Comments, questions?
So normally this overfitting here. Normally this overfitting always happens in models.
Mm-hmm.
Okay.
In the big data problems is more difficult, but when you have unbalance between class A, class B, class X, different subsamples, it can happen. If you analyze the equations that we can explain this behavior, basically the subset of samples cannot change anymore the direction of the gradient. So if you have, let's to try to have here one surface. So here basically each direction point. Let's to have here one local minima, for example. So during this optimization procedure, basically we are trying to arrive the gradient in the point that we have minimal, right? So in that case, here is the local minimum if compared to the global. When we have a small set of data, basically we have more changes in this gradient. So and we compare with the data that we have a large amount of training subsamples. Basically, this direction not represent the surface of the optimization problem. So we can explain it on mathematical way, but basically that's it. When we have imbalance of the data sets, we can suffer with this phenomenon. Good. So the next step here, basically, we change the number of neurons, the input neurons. So basically, if you run here, just to show for you that we just change the number of neurons as input, and we increase a lot on the number of parameters. So if you have here we have basically more of 200 dimensions to consider during the optimization. So uh, we needed to take care about that, because if you increase the number of parameters, it's more difficult to explain why you have certain values inside this modeling. So that's why if you can solve one problem using the smallest neural network, is much more better if compared to use deep learning, huge number of parameters. Okay, here we are defining the epochs and the batch size. Basically, we can compare the performance of these two different classifiers, right? So we build one classifier. In my example, probably you can get a different results. But basically, when we compare their Hawk curve, as you discussed during the morning, the better classifier we can associate with the more area under of this curve. So in that case here, in the orange classifier, we have, if compared 20 neurons against the 5 neurons, we have more area. In that case here, we have, if we compare the same points of false alarm, we have two different efficiencies measurements. So it means that the orange classifier is better, because considering like 20% of false alarm, we have more efficiencies for the orange classifier. So it's a good way to compare two binary classifiers. Okay. So other interesting approach that we discussed a little bit during the morning is related to the range of values for the input variables. So we need we have this parameter with this procedure to find the better weights, but during the initialization, basically we search for random values. So we have here basically in the first interaction we have a random search, random initialization, and the range of these parameters, it's important to have at least the same range of your input variables. In our case, basically we initialize using the HAL values, right? When we check in the histograms, we have the HAL values. But the weights was defined between 0, -1, and 1, because all of our transfer functions is defined in this range. So one thing that we can do is try to normalize the inputs to have better training, considering the same range of the weight. So we have a lot of other motivations, but this is the first one. So let's put all of the values in the same range to facilitate the training. So in that case, I'm applying here this norm. Basically, it's a scaling to considering the HAL values in one value, considering the minimum and maximum that belongs of this sample. So if we execute this normalization of the input variables, basically, instead to use HAL values as input, we are using normalized values between 0 and 1. So without lost the shape of the uh, sample. Let's take a look here, for example. For F length, we have the same profile. We have the same profile for signal and background, but defining the scale between 0 and 1. So we have the same shape, the same physical profile, but the values, we have this constraint in the values. So probably we have a much more better classifier because it helps for the optimization. So we don't need to deal with big numbers. It's help a lot the transition of the gradient until the local minimum. Okay? Questions, comments? Everything's fine. So we can run here again just to plot everything. So it's more one variable just to check. And here, basically, we want to run the same architecture considering now this scaling procedure in the input variable. So just to see the difference. So basically, we have this model 3 and model 4, 5 neurons in the input layer and 20 neurons in the input layer for the model 4. So I'm running here the training, and we can monitor all of these values here. So each interaction we have a different value for the accuracy that we can see that the accuracy is increasing. In the same time that the loss function, this binary cross entropy is reducing. So when we have it until 0, so we have basically one good reproduction of the modeling. Let's wait a little bit. Okay, nice. In that case here, just to get the results from these two different models, model 3, model 4. So basically what I'm doing here, so I'm getting the prediction values. So we provide the training and we have this model trained. So I want to see the results when we feed this model using test dataset, right? So applying here the test dataset in this trained model, we have the prediction of these models. So I'm doing the same procedure for these two different models. And we are applying here this function, the hockey curve, to extract the measurements that we wanted to evaluate, the metrics of our evaluation. So like fake false positive rate, true positive rate, and the thresholds to build the rock curve. That's the idea. So all of these vectors here, basically I'm using to plot. So let's do test. So we can compare, for example, 5 neurons using this scaling as input. In my case here, you can have other results. 0.83 of area, and when we compare here, let's see if we improve something. We improve a little bit, but we have some improvements, let's say. So when we do it many times, we can see statistically the difference between using or not the normalization. So it's interesting to check that we have this impact.
uh, I'm not sure if I'm correct, but I think the increase because of the rescaling was bigger in the less neuron scenarios than with more neurons. Because if you see if with 20 neurons there is 0.87, and I think the other one is
The
quite
same.
the same.
The same.
But the change in the 5 neural case was better.
Mhm.
So but I think in the 20 neural case it got a little bit better, but smaller.
Mhm.
Is that the case?
I think so. I think
Yeah.
so. It's very interesting you comment because in many cases, not important to have too much dense layers or one biggest neural network. If we prepare our data and we take care about these aspects, we can have a small approximation, a universal approximation using a small neural network that we have a very close performance.
Yeah, and I imagine that if you increase the number of neurons, the training will take longer, and probably this aspect of treating the data, it helps you to get the similar results without the need of increasing too much your
Exactly.
neural network.
Exactly. We can reduce a lot the complexity if we prepare the data, if you have good features to estimate the signal and background separation. So that's why this kind of project is very interesting for data analysis, because if we get more expertise in the data distribution, we can build a neural network machine much more powerful if compared to just to feed the data inside the neural network. And we can explain better afterwards the results. Good. So I did here another exercise. Let's see if I put it here because I don't remember.
Professor, I have a question here. How is related the ReLU, the Adam, and well, the activation and the loss functions, everything else, to the concepts we have seen in the morning, and how a developer choose one of them of those, if based on their experience, or if there is some rule or are advantages. What is the difference?
Very nice question. So, for example, if we have a classification problem, basically we want to define just possible targets, right? If we use signal as 1 and background as 0, for example, to build the distributions in the output for the neural network, we need to use a transfer function that can explore better this range of values, right? For example, let's see here, this one. For example, if we, in that case, if we define our target as 1 and 0, it's not making sense to use this kind of function here, right? Because we have the -1 in the domain. So it's much more useful to use that one, because the saturation is considering our constraint, right? So we have this first analysis to do, but we can define -1 and 1. So if we define in that way, we can use this function here, but we need to remember that we are deal with the gradients, right? So considering this kind of a function here, we have more smooth transitions for the impacting of the flow signals inside the neural network. So we can associate with this. And if you have a regression problem, so considering the regression problem, we have a wide range of possible values in the output. I cannot use one function that we have constraints. For example, I wanted to provide a mass regression, so between 0 and a certain value. So I needed to use some linear or some approximation of this expected curve as a transfer function to consider. So it's very interesting because you needed to reorganize your code based on your problem. And in terms of the optimization algorithm, also it's depend of the problem, because we have a different strategies in mathematical optimizations, like the scaled gradient algorithm, algorithm that we provided the inverse of the SCN matrix. So depending of the number of variables, for example, algorithms that we need to inverse the SCN matrix, we spend a lot of computational costs to invert the SCN matrix and provide the gradient. So the second order algorithm is very difficult to solve batch by batch. So for this kind of, if you have 100 variables as input, using this kind of algorithm is maybe is difficult. We can use different ones like it is Adam, it's more stochastic algorithms for searches and so on. So we needed to think about these aspects when we include these boxes in the neural network. Nice question. Yes, it's very interesting. Unfortunately, we don't have time to explore all of these details, but we have all of these aspects, let's say, to deal. Okay, so the last one, I think will take more time, but I want to run with you here. Basically, this box here, we are setting our cross-validation procedure that we discussed during the morning. So let's go through into the code. Basically, to use the cross-validation strategy, I am using this function here in the line number 6. So we have this stratified k-fold. Basically, we are splitting our data on a number of folds. And after that, we are taking the same amount of examples for the signal and the same amount of examples of background for this fold in random way. So we are taking for all of these folds. And for each fold, we will do also many initializations for the same model. So we wanted to estimate first the statistical fluctuation of the data set. And also we want to estimate the statistical fluctuation for the optimization algorithm. Why we want to estimate that? Because all aspects that we already discussed. If we split in the random way the data set, we don't know if we affect or not the PDF of the variables. So we want to investigate different combinations. And considering the stochastic procedure to start the weights for the initialization, I cannot guarantee that when we start the weights, we will arrive in the global minimum. So I can arrive in the local minimum. So, and then to take care about that, I start the optimization in different regions of the optimization surface. If I have luck, I will arrive in the global the global minimum. So I can analyze all of these uncertainties using the cross-validation procedure, right? So using this stratified scaffold, basically defining here the model. So we use just one simple model with 10 errors as input. And here, basically, I'm mapping, getting the target and the input data. So defining here the number of splits, so 5-fold cross-validation is split in 5 subsets, and 5 initializations for each combination, training test. And in this line here, 37, basically we have all of the index that maps this part of this training, part of this test samples inside the folds. And we use this SKF to select. You use this index to select the training index and the test index for each training. So basically, we have all the subsets for each rotation, and we start the training. Basically, these 2 sequences of 4. The first, the more internal, initialize many times, five times the same model, and the more external loop we are changing the subset of data set. And after that, basically, we are getting these evaluation metrics, and that's it. So just for comparison. So, but in that case here, I provide a piece of code to compare everything. So, unfortunately, it will be spend a long time. We can just wait for the results. But basically, usually we have a strategy to look for the uncertainties. So we have here a box plot for each fold until 5 folds. And we have for each fold 5 results, right? Because we have 5 initializations. So we can analyze these box plots to try to see the impact of the uncertainties between the folds, the impact on okay, we can define the AUC for metrics, or we can define a fake rate, or also the loss function. It is a very interesting diagram to check after the training. Okay.
I'm not sure if this part of the code is on the archives. I don't know if anyone could check if.
Okay, maybe it's not updated, right?
I think so. The last one is, but I think this cell is not.
Okay. So I needed to update in that case. Good, I will do it because for tomorrow it's good to have this piece of code there to for the other examples. Okay, I will try to make this second talk. Let me see if you have here. No. The second part of the talk to discuss about the deep learning. We already saw a lot of aspects for machine learning, so it's important to discuss a little bit about this matter that we have now. That today is more discussed in the academic program. So, which difference we have between the machine learning, deep learning? So it's interesting to discuss. So it's very recent publication that we have the starting of the deep learning investigation. It was in 2016. Basically, we have this both a good fellow and a Hinton published some set of algorithms that combine many layers for one single model. Of course, it was possible because we have the hardware evolution in these last years. So it's possible now to train a neural network machine because we have more memory, we have more space, we have fast CPUs to compute these gradients and so on. And Hinton and Goodfellow provides a lot of new algorithms and new optimization algorithms for some imaging processing and face recognition and objects detection. So we have this good book, this introduction for the deep learning that basically explain that we have one problem that we discussed during the morning. Basically, for the machine learning side, we needed to invest in the featureization, right? In the feature selection and feature implementation to get the invariant information from the data. In many cases, in many big data cases, it's very difficult to do that. the task for the deep learning is try to embed this stage inside the neural network machine. So if we have a neural network machine can do the feature extraction inside that, probably is more powerful if compared to this human annotation. So we have some examples that it's working very well, but we have other examples, mainly in the high energy physics, that human annotation based on the expert acknowledgement is more powerful if compared to the automatic featurization. So we needed to take care and compare our all of these results. So here the main difference in terms of architecture that we can describe. So in the machine learning area, we have this feature extraction stage. And the deep learning, basically, we have the feature extraction inside of these huge layers of neurons. So Hinton and Goodfellow managed to demonstrate that considering many layers, when we analyze the content of these weights, basically we have a strong correlation with the features, discriminant features that we expect in the data. So we have the invariant information encoded inside the neural networks. It's difficult to infer it, but some experiments it was possible, mainly imaging processing. So let's to take a look in the one of these deep learning machines. Let's call it the convolutional neural networks. So basically, we have one strategy to make like a signal processing for some details in the input signal to try to extract the differences that we have between the samples. So the idea of this CNN is try to make one extra layer to make these representations in multiple levels of representation. So I have one example here to make more clear. Basically, let's to think about one task for image recognition. So I have an image, so it's 2D dimensional. I can apply a sequence of stages to try to get the main features of this image. So I can define here one region, and I can apply one filter using this convolutional operation to build a new map, and I can use different filters to build different maps. So you remember in the Instagram, for example, I can apply different filters, right? I can have the same representation for the image in different perspectives and different colors and so on. So basically, we are applying there one convolution mask to get different representations of this image. And we can reduce this dimensionality. Basically, this pooling here is one strategy to reduce the number of dimensions of this image. And we can have it for different scales and different levels. And we can feed all of these features in one common dense layer for the neural network to get the nonlinear correlations. So we have a sequence of procedures to extract the main features, and also we can combine everything in one convolutional, in one dense layer to get the nonlinear correlations. It works very well for many problems. I will pass by because I think we don't have too much time to explore all of the mathematical definitions, but it's just the definition of the convolution. So we have constant filters that we can learn during the optimization procedure, these weights for these filters, and then we are passing to try to get the main variations of the signal or these metrics if you have an image to make the pooling sequences and so on. Basically, we have this linear combination. Basically, it's the same procedure. So if we have an image, basically we can define the size of this filter, and we do this Hadamard multiplications to have the linear combination when we pass this filter for different sections of the image. So it is very interesting in terms of applications in calorimetry. For example, if we wanted to let's to try to consider that we have a calorimeter with different cells, and we want to consider it as image, right? Usually we consider it cell by cell, but we can consider as image. And for EM showers, probably we have more consistent deposit of energy in the calorimeter, so for incoming particle. For hadrons, for example, we can have more spread showers. If we consider it as image, maybe we can build one CNN to try to identify the difference between the EM and hadron showers. So considering all of these usual neural networks, maybe all of these features can be encoded inside of the neural network. So we have some exercises using some simulators using the CNNs, but we needed to take care about that because it's necessary to include a lot of constraints and a lot of assumptions during this neural network building. So here, one of the more classical architecture. So we have this demonstration in the book from the Goodfellow book. So this exercise to recognize the letters. So we have the featuring maps step. So basically, we have the filters here, defined filters here that we define as first a size of this kernel, and then we have the subsampling step to reduce the dimensionality of these previous featuring maps. And we can also apply different filters to exchange to extend how many maps we want. And after that, we can just to serialize all of these features to input in one fully connected dense layer. So we can define many steps to access the invariant information present in the data set. Okay, professor. We can use it just in images, not we can use also in one single vector because we can use the 1D convolution also. So we can have a 3D convolution, right? Because we can have a three-dimensional convolution, and we can have any dimensional convolution also, plugging different kernels, different filters for the dimensionality that we want. Of course, the training is very much more difficult to do in that case because we need to optimize all of the weights for these filters, basically. So afterwards, you can check the details that they put here. So I will pass fast just to show for you all of the steps. So as I said, we have this nonlinear, the linear combination to extract the filter maps. We have this matrix multiplication, right? So we will map this window in one single feature afterwards. So we have one compactation each step of the applying filters. It's good because we can control the dimensionality. because if you remember of this section here, when we increase the number of neurons, we increase the number of parameters, so it's more difficult to train. And then in that case here, all of this convolutional processing, we can reduce the dimensionality.
Just
So
just a question here. So what is this kernel exactly?
kernel.
Yes.
So basically, if we go back, so this is the input variables, right? A, B, C, D, E, F. And basically we will multiply these values for some weights.
Mm-hmm.
This weight is the kernel. So
Okay.
this W here, W, X, Y, and Z.
Mm-hmm.
So these values we needed to define. And during the backpropagation, we will update this value.
Okay. So in the case of the calorimeter, the input would be the energy deposit in each cell. You have a kernel with the weights,
Yes, these
and
weights we will
they are
optimize.
being updated to okay.
Yeah, yeah. We can have a different set of weights for all purpose. Let's to remember for the Instagram, for example, in this image here, we can remember about the different purpose of these kernels from the imaging processing area. So if I want to make like black and white processing in one picture, basically I will apply one kind of kernel. If I want to detect the borders or the edge, so I can apply one single kernel that basically we will try to put more values when we have the transition of colors, right? When I want to detect the borders or the edges, basically I want to highlight this section. So when we have the transition of the colors, I put more numbers. In that case here, for example. So if I wanted to blur the image, basically when we have the transition of the colors, I just to compute the mean and I replace the number. So look that this kind of strategy can include different impacts of in the image. In our case, in particle physics, we want for this photon hadron separation. Basically, we want to understand the spread of the shower in the lateral direction and also in the perpendicular direction. So we need to think about which kind of filter we can implement. We can put non-trainable, for example, fixed, or we can leave for the neural network machine to try to understand. Okay, good, interesting question. Yeah, in fact, this kernel play an important role in the CNNs. So here we have this basically very simple mathematical operations. So we have these multiplications between the input and the kernels, and now we need to. It's just a representation of the multiplication of a matrix. So if you reorganize our tensor or vector for that multiplication, so we have this sparse matrix. So if you have a sparse matrix, we can consider that the numbers that you have in the kernel, we will make the relationship much more powerful with the input because the other value is zero, so that we don't care about that. And we have many engineering solutions to deal with some problems. For example, if we define one size of the filter, so when we pass this filter here, make this convolution. When we arrive here with this filter, when we jump for more one step, we have pure zeros because we don't have any more signal in this column. So we need it will impact in the dimension of the next matrix, right? So we needed to take care about that. We need to define some rules to force the dimension that you want in the next step. So basically, I can if we define one filter with the size of filter too much, so I cannot pass this filter for all of these numbers in one fair way. I can provide more multiplication for some numbers if compared to the others. It means that I will pay attention just to one section of the image if compared to the whole image. So it can be a problem. And then when you are building the CNN, you need to define the size of this kernel to avoid to have some just to look in the pieces of the image. So we want to build one fair comparison for all sectors of the image. So we have this basically uh, the organization of the features. So we are passing the filter to convolute with the matrix. So I have one correct position to store this number, and we have different filters, and we can do different movements for this convolution. So, but basically, we can just to investigate which kind of organization we want. So, and to reduce the dimensionality, we can also select a different strategy. So, for example, we can define the max pooling strategy. In that case here, we in this area, basically, I will save the maximum number that we have. So in that case here, we have 4, and then I will provide one new matrix with this new value. If we remember the difference between uh, the 4K image and in the high definition image, for example. So we have too much pixels in an image if in the 4K image, for example, if compared to the high definition one. And we can basically jump for the 4K until the high definition to reduce the definition of the image. Basically, what I'm doing it. I'm saving just some pixels, the most representative pixels, and we are reducing the resolution to arrive in the lower resolution, basically. So we are talking about here for resolution. So one strategy also is to compute the mean. I can compute the mean and associate the mean there. So I am saying the image with different resolutions, basically. It's very interesting strategies because once we have a lot of different features, I can explore different features, even we have the decrease of the resolution, basically. Okay, some applications, for example, today for the autonomous driving, we have a lot of deep neural networks and convolution networks being applied in the automatic cars, for example, because we have this output segmentation of objects, and it's very powerful to run online because after the training, so it's just to execute, and it's not so usual to execute. We can embed this in the driving, in the computer for the car. So many factories is using this strategy for car segmentation. And in high energy physics, so we have a lot of papers, interesting papers, to using the CNNs and try to understand after the training how the profile of the kernels that the training observed at the end of the procedure. So in that case here, it's using one technique called deep set. So it is, if I'm not wrong, to make the jet constituent procedure. So to try to define a different flavors of the jet, the hadron KCD jets. So it is very important in top quark stuffs and hadron in KCD investigation, because we have a jet of particles, we have a different constituents and different combination of quarks. For example, we need to disentangle everything. So we can consider it as an image in the calorimeter, considering a lot of assumptions for the track reconstruction and so on. And in that case here, these guys provide a application for deep sets, considering the CNNs for jet reconstruction. And they have also the application for the Turing Cove telescope. Here, in that case, using the image directly from the Turing Cove telescope. So it's not using the HELAS parameters, but now looking for the projection of the map of this Turing Cove telescope. So they have a lot of image processing here, because usually we have this hexagonal dimension of the Turing Cove telescope, but we needed to normalize this image for the same resolution, right? So they have this processing and this rescale, and after that, here the procedure basically, and after that, considering all of the machinery for the CNNs to build a classifier, and a lot of comparison here. So it's very interesting paper to check. I think it was from the Hess telescope in Namibia, I think. Okay, here I think we can finalize for today. Tomorrow, during the afternoon, we have this big computational exercise, and basically, I will ask for you to make small groups to try to develop some challenges that we have. Basically, I will provide the data, and the idea is to try to make all of these different architectures and provide the comparisons using the cross validation procedure, changing the optimization algorithm. So it's a practical exercise just to have from scratch one implementation of the neural network. So that's it for today. Thank you very much. Questions, comments, additional comments? If not, I think Bertrand, yes.
I have one comment concerning the deep learning, where you hypothesize basically that you can learn the data preparation basically inside the network. I think we have many proofs now that we can usually do better than that if we input not only our understanding of the data, but the fact that we have, or maybe this is connected, we have a model that we can use to let's say to understand
fit.
what is in our data, and we in that case we go from a correlation that can exist among the data to a causal relation. And it seems to me that this is something that we can do as a physicist using the models that we have, while the any convolution neural network, if any deep neural network can not do. And what is your feeling about that? And what can we do as physicists there?
Yes, for sure. I think we have this good example for our colleagues for Grenoble to to try to parameterize functions to make the relationship of the position of the particle in the calorimeter and the profile of the shower. So this eta notation stuff, including the in the middle of the neural network. So we have some expectations, and we can use these expectations to fit curves to help the learning machine. So I think it's very, very powerful if compared to just to use current common architectures to process the data. So we have also other examples. The impact of just the impact of the organization of the data uh, uh, in the input of the CNN, for example, we have different results. For example, we have a student that is trying to understand the impact of cross-contamination of the sensors, because we have an incoming particle. This particle can, the electrical field can perturbate the signal shaping for the neighbor cells. And okay, we think about one image to fed off this CNN. So depends of the size of the image or the organization of the pixels. We have different results. So we have a results, for example, that looking for different perspectives of this image, we have additional performance at the end for the training. So we need as physicists to think how we can help the neural network machine to converge. So we needed to think our expert acknowledgement to live and building features or put constraints in the training or even build transfer functions much more closer to our models if compared to these common standard configurations. Yeah, I agree.
And maybe a last comment on that. Among the latest improvements that were done in our fields, there were some attempt to use what we know from the dimensionality of the objects that we measure. So, for instance, if we have an electron, for instance, for which we have the energy px, py, pz, in fact, we know that there is a relationship between the energy and the momentum, which is related to the Lorentz invariance and this kind of stuff.
Mm-hmm.
And there are a new type of network which are called equivariant networks, in which we impose the fact that when you input some objects, for instance, like for momentum, if you make a transformation on those objects, it should not change the results, because physics is invariant under Lorentz transformation transformation, sorry. And then it means that if we do not build the neural networks so that it is guaranteed by construction, then we are losing something. And it turned out that there were major efforts to turn to develop methods that allows to impose some symmetries of the problems that we need to deal. And usually you gain a lot by doing that.
Mm-hmm. Thank you, Bertrand. It's a nice example. Yeah. Ricardo.
This remind me of something I saw a paper that they impose these physical features, like for example, energy conservation, momentum conservation in the loss function, and they improved the minimization of this loss function and the physical reliability of the data that they generated, for example. So yeah, it's an interesting discussion to implement this physical view
Mm-hmm.
into this machine learning processes.
Yeah. Recently, not recently, but I think 3 years ago, 4 years ago, we had one publication called Physics Informed Neural Network that let's see here, I think is Let's see if I can access. Yes, this one. It's very nice paper. Basically, it was one uh, one new architecturing to, in that case here, to test inverse problems. So basically, this architecture include in the, let me see if I have here. We don't have the boxes. Let's see here. Basically, during the optimization, we have all of the details for the differential equations being solved during the optimization algorithm. So for thermodynamic applications, for example, we have a lot of different equations that we can describe the phenol. So we included all of these equations in the optimization procedure. So we build the function, the differential function, to be optimized during the training. So it's a very nice application that now is applying for different variants of problems. Let me open here. It's very interesting for us. This architecture here. Basically, we have one dedicated fitness function, for example, here, that we can consider different differential equations directly related of the model that we are exploring. So at the end of the day, we have a function to estimate everything, but we can, based on our acknowledgement, we can build this function inside of the neural network. So it's very powerful for these results here that we have different variants, like different architectures using the same concept. That's it. Many fields, many applications, and also many results. But in that case here, for pins and also for custom, like Bertrand said, custom CNNs, it's much more easy to explain the results, because after that we can check the filters, we can check the kernels, we can check the variables that the neural network learned inside these differential equations, and then we can compare it with our model. So if we not apply this strategy, probably we cannot explain anything. So, and we can have good results, but we cannot explain these good results. I think we are in the same situation at the end of the day. Bad situation, let's say. Okay, good. So see you tomorrow then. We have the section at the second part of the afternoon. Okay, Gabriele, you provide more details. But for today, that's it. Thank you again.